I want to know what's going on with this. Jolie, what's the first answer and why?
It's 3/5.
It's 3/5. Very good. Now, oops. Now, how about the why part of that?
Because they're going up exponentially at the same rate.
Whoa, that was
Okay, yeah, so it's.
Actually, they're going downward.
There they are. What else?
So they cancel.
Okay, yeah, it's 3/5 because the polynomials are of the same order, top and bottom, and when that's the case, when we're taking an infinite limit, we take the ratio of the leading coefficients, right?
yeah.
So when these match up, we just do that, right? Does it matter if it's approaching negative infinity or positive infinity?
No.
Does not. Does not.
What if the 7 and the 5x cubed switch places? Do we still use the coefficients or?
What do you mean if like these were written out of order?
Yeah.
Okay, good question. So this always presumes that we are writing the polynomials in standard form, in other words, correctly. So we're writing them in decreasing order of powers, right? So no, it wouldn't change because it would still be the biggest power of x is going to be the dominant term. But you always want to write the dominant terms first for that very reason, okay? All right, so yeah, this one does not depend on the what direction you're moving because the asymptotes. What I want you to see here, and this is kind of an important connection, when we do something like this, remember that the asymptotes are shared. So if there's only going to be one asymptote, we don't know what's going on in the middle, but out at the ends, it's going to stick, both ends will stick to the same asymptote, right?
Yeah.
Okay? All right. Next one. Let's see, April, what's going to be the answer to the next one?
0.
0, good, how come?
Because the bottom is increasing more quickly.
Good. Bottom's a higher order polynomial, so it's going to get big faster. And so this goes to 0. Once again, does it depend on whether it's negative or positive infinity?
No.
Makes no difference. Okay, yes?
Does it matter? Are you going to want it to like tell you if it's leaning more towards the positive or the negative of a 0?
Doesn't make any difference because really the only reason that would be an issue would be in one like this where there's a big difference between positive and negative because one of them is like infinitely far up there and one's infinitely far down here. There's really no significant difference between 0 plus and 0 minus. They're both 0. It just means that the asymptote is going to be on the axis. Does that make sense?
Yeah.
But we still don't know if it's above or below.
This one?
On it.
We don't care.
Oh, we don't.
We don't care. It's not important.
But what if we?
You only need the 0 plus when you're dealing with
Okay.
Yeah, the 0 plus would be, that was crucial to us only when we didn't have our tricks yet, right? And we had to figure out what was going on with these, right? This is going to be, I'm kind of let the cat out of the bag here, but what's going to be the answer to this one? Okay, we know we're going to get infinity, right? Because the top, we don't know which one though. I mean, you're probably right. I haven't even looked. Top is more powerful than the bottom. Listen, please. So it's some kind of infinity. How do we find out if it's positive or negative? Yeah, we're just going to look at all that stuff right there, right?
Yep.
Whatever the sign is, whatever the sign based on the dominant terms of the top and bottom is going to be, that determines the overall sign, right? Because all this stuff over here doesn't even matter, right? When we get out to really big values of x, it makes no difference. So what are we going to get here? It looks like we've got a negative value of x, so we'll just evaluate the signs of the top and the bottom. What is negative 4 times a negative value of x cubed? Positive. So the top is positive. 3 times a negative value of x squared. Positive. So positive over positive is positive. Okay, we got it. Right? Okay, let's do another one. How about, see how we handle this. What if we've got, okay, so our goal here here is we want to get this to a point where we can do this quickly, where we don't have to show a bunch of work.
I think
I
I
like
know
that
the
for you.
answer.
Plus,
off the
yeah.
top of my head.
3 square root of 5.
Well, there's gonna be a, what's it called?
Absolute value.
Thank you, Patrick.
I bet
Okay.
it's 3 over the square root of 5,
Hey.
and then we do like radicalize that.
Oh,
3 over the square root of 5.
We're supposed to be
Well,
able to achieve together.
we'll check that out.
Plus or minus, isn't
Yeah,
it?
well, it's gonna be one or the other.
Oh.
So here's what we gotta look at. Okay, we need to look at just this stuff again, right? Because whether it's inside a radical or not, we know that the dominant term is the only significant player in the top and the bottom here when x gets really big in the positive or negative direction. So these guys go away, yes.
Are we ever gonna get a radical problem where x is greater than squared?
I mean, we could do one. It's, you know, probably
Because right now
not.
we do x squared.
Yeah,
which is
that's-
the absolute value of x. But what would you do if it was bigger than that?
Okay, so if it was bigger than
That's
that,
5x cubed.
then like if it was the square root of x cubed, you mean?
Yeah.
Then that would be like an x to the 3/2. That gets a little bit messy. We won't do that probably this year. I mean, that'll be something that you'll see later. Okay. All right, so what about this? Now, what is this gonna look like then? This is gonna be in the limit. This stuff doesn't matter. So we've really just got the limit of 3x over, what are we gonna get on the bottom?
Square root of 5 absolute value of x.
Good, square root of 5, absolute value of x, as x approaches negative infinity. Now, the negative is important, right? So,
Negative 0 squared.
okay, good. So we know that the x's, when x is negative, right, what does the absolute value of x become? And we gotta think back, before you answer that, think back to our piecewise function. What do I fill in here? The absolute value of x equals x when? When it's positive, good. When it's positive, the absolute value does nothing, doesn't need to, right? It's already positive. What does it do when x is negative? How does the absolute value function make it positive?
negative x.
Yeah, we need a negative x, because negative is positive, right? So this is gonna be what's going on though, isn't it? Because we're less than 0, way less than 0, right? So we would replace,
So,
make that replacement, right? And we'd end up with the limit of 3x over square root of 5 times negative x. And yeah, those are gonna give you a negative 1, aren't they?
so how are you gonna get?
Everybody see that?
Yeah.
Combined, those are negative 1, and so I just get a negative 3 over root 5.
Do you want us to rationalize?
Yeah, I mean,
that?
probably, just the question we'll ask you, tell you to rationalize, simplify it if you need to, or rationalize it. Probably it's not a bad idea to rationalize.
Wouldn't it-
Okay, yeah.
So like on the one we did yesterday, like I thought the answer was like
So you can
so where does the infinity come
Oh, not, on these it's not infinity.
from?
It, these ones it wouldn't be infinity, because remember what we're doing with these? Remember we took a look at this function? I wish I had that graph, but I don't. Remember we looked at g of x equals either the absolute value over x or its reciprocal. And what that ends up looking like, anybody remember what that function looks like?
Which function?
No.
That one?
Isn't it like?
Does the circle out?
Okay, yeah. When x is positive, it's equal to 1. When x is negative, it equals negative 1. And so really all we're doing is we're multiplying that function by 3/5, or 3 over the square root of 5, right? Which is going to be, that's going to be just a little bigger than 1. So ours is going to look not like this, it's going to be just slightly taller than that, right? And so when we're taking the limit at negative infinity, this is going to be the y value, isn't it? Because the y value is the same, does that make sense? Every place to the left of 0. So that's why we get the negative value. But you don't have to draw that.
But then how is the negative 3 over root 5 like a limit? If it's a straight line, it's always on that line.
You're right. So the limit, think back, and we haven't talked about this in a while, but think what a limit means. The limit is just where the calculus ant thinks he's going to step when he gets to a certain value. So as the calculus ant walks along this function to the left, he always thinks he's gonna be at what y value?
3 over 5.
Yeah, negative 3 over the square root of 5, right? So the function is horizontal, so the limit's just constant, right? Okay. Make sense?
I'm so confused about why the 3x wouldn't be a negative 3x to make the thing positive. X
It
equals
is.
negative infinity?
Well, no, it's not, because x is a negative value, right? And so when we plug a negative value into x in the top, that would give me a negative number on top, wouldn't it? Right? But the bottom is a square root of 5 times an absolute value of x, right? And the absolute value of x, if we want to write that as a piecewise function, we have to write it in two pieces. For all x values where x is positive, the absolute value of x would just equal x. For all values of x where x is negative, the absolute value of x equals the opposite of x. Because we are in a part of the domain where x is negative, we have to replace the absolute value of x with a negative x. If we didn't do that, when we substituted, we would get a negative answer instead of a positive answer, right? Now, you don't really, I just wanted you to see the behavior, but really you could even just look at it here, couldn't you? Right?
But how come you don't put the x in for the top x too? You just put it in for the bottom.
Because it's the square root of an x squared.
Well, we never really put the x in. The x's are just canceling algebraically, right?
The x is in the absolute value.
Right, the x is inside the absolute value, so to write it without an absolute value, we have to write the x outside of the absolute value function, it's gonna have to be one of these two things, right? Which one is it? Well, because we've got negative values of x here, we have to replace it with an opposite of x,
Okay.
or negative x. You could, and as you get a little better at this, you probably could even avoid that step, right? And just look at this and say, okay, well, x over the absolute value of x. When x is negative, I'm gonna get a negative over a positive, which is negative 1. See what I'm saying?
Yeah.
So you can, I mean, as you get more algebraically, this is the correct way to do it, right? But you'll be able to maybe take that shortcut here once you get a little better at this, right? And you're more comfortable with why that's the way it is. Does that make sense? Okay, let's do one more of those. Because those are the hardest part of this section, is this stuff. But that's not too bad. I mean, it's-
I like these. It's not
Wait, we did this yesterday.
That exact one?
I think so.
Serious?
Oh no, you flipped them.
No.
My bad.
So,
I'm on a different page.
that's the value of the x.
You're gonna get the absolute value of x over 3x. Oh my god, right? Yes, straight fire. You're gonna get the absolute value of x over 3x.
I already got 2 out.
Okay, so what do we got? We know we've got positive values of x, right?
Yeah.
So then we can rewrite this as the limit of, what's that gonna be?
Absolute value.
Absolute value of x over 3x. And for positive values of x, what's the absolute value of x equal to? Positive x.
So then it's just gonna be
One over
infinity. Oh, just kidding, no, sorry. I was thinking I
So what's it gonna be? 1/3. 1/3 positive infinity is close.
Well, at least you got the positive right.
Yeah, there you go.
She was close, right? She was on the right
I knew it was
side.
positive.
Right track, wrong.
She was at the right side to the right side of the X path.
Okay, I wanna go back a little bit and let's go back to this example.
Keep waiting for it to be difficult for some reason.
This example right here.
Yeah, if you make it, yeah, it starts to get hard.
I know, I'm waiting for it.
lynching.
It's a safe space.
Fix it, like a safe space thing on the wall. Fix it.
Did you really?
Yeah, like on the left. It's like it would be up there. Fix it. It's just like a safe space. Post on the wall.
She also has that changing
It's like,
picture that
it's
it
not,
took us forever to
it's not
figure out.
exactly safe space. It's like, this is a safe environment for students who.
No, that picture that changed clothes and walked in, it took us forever.
Okay.
There's a picture.
That changes season.
Yeah.
You
It took us forever to figure it out.
Just 2 weeks ago, I know.
guys didn't.
No, we figured it out like 2 weeks ago, so yeah.
I remember noticing you back and forth.
Okay, we already did this one, right?
Yes.
We got an answer of positive infinity, I think, right?
Yeah.
Okay. Okay, there's something we can do better with this though.
Better.
Yeah, thank you. Okay, so we can do something a little better than this because, and I'll tell you why this is, and then you'll see what happens. But whenever you get a polynomial on the top that is exact, whose order is exactly one bigger than the order on the bottom, we can do something with this. Let's go back. We got to review a little synthetic division here, or at least long division, not synthetic division.
Wait, is this easier than what we've been doing?
It's no harder. I mean, it's no harder. Okay, so
I like math.
okay, quick review. We haven't done this in a little while. Can we use synthetic division for this one?
No.
We cannot. How come? Well, it wouldn't matter that, but there's something about this, something about the denominator.
The bottom is polynomial instead of just like a 1 degree.
Okay, the bottom is not linear, right? So we can't use synthetic division, unfortunately, because that's easy to do. So the only alternative is we've just got to use polynomial long division. Okay, so let's write this out. Taking this right, yeah. Okay, a couple things I want to remind you of with polynomial long division though, because it's been a couple of years since probably we talked about it, and you probably talked about it last year, but it's been like a year since you talked about it last year too. So when we do polynomial long division, remember that inside the, I don't even know what that's called, the division sign.
Inside the.
Anybody know what that is?
Looks exactly like the square that we signed you made.
It looks really close, doesn't it? Inside the long division sign, which has some fancy name that I don't know, you got to make sure that you leave a column for every power of x, right? Otherwise, this can get confusing and it's,
Real quick.
right? So then, plus 0x plus 0, right? Did I mess something up? Oh, yeah. Okay, in this case, it wouldn't have been as big a deal because the two terms that we had were sequential. But what if I'd had like an x cubed term and an x term? Then I would have had to include that 0x squared column there, right? Okay. All right, so remind me how we, oh, this is going to be horrible.
No, this isn't bad.
Okay.
Maybe we shouldn't do it.
I like these.
I think we should
Fun.
just-
Oh, this won't be that bad.
No,
You like this stuff? Okay, Janelle, what do I do first?
Oh gosh, what is it called? Okay.
Because you're so
How
excited.
many times 3x squared goes in negative 4x cubed?
Yep.
Isn't it?
That won't be
1x?
bad. It's going to be, well, negative 1x, right? Yeah, so 3 goes into negative 4, negative 1 times evenly, x squared goes into x cubed, x times, right? All we're really doing is just to find out what goes there, I'll only do this once, but all we're really doing is we're just saying, what is negative 4x cubed divided by 3x squared? Thanks, sir.
We don't do this.
Okay, so everybody agree that we just end up with negative,
1x.
I'm gonna get negative 1x, right? So that's all that goes in there evenly. So we're gonna get a negative x if I, hang on a second. No, we're not. This is why this is bad.
Wait, no, don't you just times through and like and then subtract again?
So okay, so Yeah, this is gonna be a really horrible one. I just didn't really pick this carefully.
Oh, it's fine, do it.
Keep going.
I don't really,
Don't
I don't want it. Okay, did you guys see why this is so bad? I didn't really plan. Okay, it's so bad because it doesn't go in evenly, so I'm gonna get fraction.
We're calculus, should be able to do fractions.
Well, I know, but the fraction's gonna get carried through quite a ways.
Let's just not do it.
I'm gonna pick a better one.
Just pick one with all even numbers then.
I'm going to. I want to pick a better one. I'll cheat and use the book. They'll have a good one. Not that we couldn't do it, but it just would take more time than I want to spend.
Throw it down, problem.
Thirty only
So what is the answer for that one, negative x?
No, it was not negative 4/3 x. Okay, let's do they give me one? Yeah, they not give me one. Oh, I know why. It comes up in the next section. We'll do it now. There we go. Okay, yeah, this is a better one. Let's do this. I'll make this better on 2 levels.
Taking care of business, isn't it?
Well.
What came to mind?
Okay. That's a better one. Okay, it's better. We can also use synthetic division here, right?
Oh, it's just easy.
Okay. So how do I do synthetic division with this one? Okay, I make my synthetic bracket.
Yeah, do you have 2 on the left side?
Yeah, 2.
2. Okay, why 2 and not negative 2? You're right. Good. Because outside of the bracket, we're finding the 0 of the denominator, right? See what goes here?
Negative 4.
Okay, what if that term had been missing?
0.
Would have been 1, 0, 4, right?
Yeah.
Okay, good. Put my remainder box there, right? And this is pretty quick. What happens?
Drop
Drop the
1.
1 times
Get 2, get 2, then get 0.
Right?
Yeah.
And, okay, do I add or subtract? Add. The opposite of what you do with regular long division, right? You add synthetically, you subtract using long division. Okay, so what's that mean? Remainder of 4. Okay,
And then x.
what does this part mean right here?
And then you
Good.
you got.
Okay, x plus 0 plus remainder 4, right? So that means it's 4 over the denominator.
Yeah.
Okay, so this is equal to x plus 4 over x minus 2. That's what remains over the denominator, right? That's what the remainder is. Okay? Okay, why did we do that? Why did we do that?
Because you felt like it.
Because I felt like it, sure.
It will simplify the problem a
Okay,
little bit.
it does. It does, because now when we want to take the limit of f of x as x approaches 0, we can use this version instead of this version, which is useful. Here's why.
How was your business?
As we approach,
Sorry.
Base is 0.
okay, good. If we approach plus or minus infinity, it doesn't matter.
You're gonna get 0.
Yeah, this term right here is always going to go to 0, right? That's one of our 3 types that we know how to deal with just by inspecting. So the answer is the limit of this function as x approaches plus or minus infinity is x. Okay?
Wait, I thought, why? How can you get to 0 when it goes 0?
Say it again.
Wait,
Wait, but what if you get a different answer if you just did it
No,
in
no.
reverse?
the answer to that term is 0, right?
Okay.
Okay, now everybody, I need everybody's attention up here. Nobody's talking, everybody's looking up here. There's too much, I gotta get total focus on this. So, all we did was, in this one case, which we'll see why here in a second, you can tell me why. Because the top was one order bigger than the bottom, we divided out the polynomial because it was convenient to do so this time. Last time it wasn't very convenient, this time it was. And we got this result, right? So we wrote this as a simplified polynomial plus some remainder, right? Well, when I take the limit of this new function, right? The limit of x is not going to go away. That's going to be infinite. When x approaches positive infinity, it's going to be positive infinity. When x approaches negative infinity, it's going to be negative infinity. But the limit of this second term, because the bottom is a higher order polynomial than the top, right, goes away. Everybody agree?
Yeah.
Okay, so this didn't tell us, the answers are still the same as they were before, meaning the right asymptote is going to be at positive infinity and the left asymptote is going to be at negative infinity, but it gives us a very distinctive picture of how they do that now. Because look what this means. In the limits that x is very big, the function just becomes x. Well, what does the function y equals x look like? Yeah, it's just a diagonal line with a slope of 1, right? So look what we can do then. We can graph this thing with kind of an envelope that describes the function. Way out there and way over there, right? What's going on in the middle? Who knows?
Who cares?
But when you get to the edge of the function, you know that it's going to stick to this slant asymptote on the left, on the right, and on the left, right? So that's what we call this. This is a slant asymptote.
Is that what all of them are when it's like one bigger than?
Well, the ones we've dealt with previously have always either been vertical asymptotes, right? And those are just where we get zeros on the bottom, right? Or they've been horizontal asymptotes, which we just got introduced to, and that's when we take a limit and we get a constant answer, right? So if we go back to that first slide we looked at today, these were horizontal asymptotes, right?
Right.
And this one is infinite at the ends, but we know more than that. If we divide it out, we actually get a function that it's going to appear, that it's going to be like when x is really big, positive or negative. Because this term will just be insignificant, and this is the term that will dominate, but that's a predictable function. It's a line.
Wait, so where would the green function be in comparison to the slant asymptote?
So, okay, so the green function, once again, the green function is going to do probably, potentially, some interesting stuff in there that we'd have to go find out. Okay, but we're only looking for the behavior at the tails here, right? So at the tails, it's going to stick to this, you know, up here to the line on the right and down there on the left.
So it's gonna like follow up with that.
Yeah, it's gonna get closer and closer and closer, and it's gonna, you know, stick to the asymptote but never quite get there at the ends, right? Does that make sense?
Yeah.
Okay, so why don't we just do this one and see what happens? Let's see what happens with this function if we do the whole thing. So we know that the slant asymptote is the function y equals x, right? Let's do the rest of the calculus and fill in the blanks. Okay, so can we rewrite that one? What? Remember that. Minus 2x plus 4. Okay.
Why don't you just copy?
Yeah, because I had a bunch of other junk on it.
Oh, okay.
Minus 2x plus 4, I said?
Yeah.
Plus
No, don't do that to me.
Thanks, man.
Okay, so there's my function. Let's go ahead and find all the relative extrema, the points of inflection, all that good stuff. Make our table. Okay, so what is y prime here? Quotient rule, right?
Can you do like synthetic division to get it simplified and then do?
You could.
You could?
You could, but, okay, Riley asked a good question. Could you do synthetic division to get it simplified first and then?
But it doesn't work on that.
Yeah, but the problem is then, see, you've got this other, right? You're almost better off, well, I think you are better off, just leaving it as a rational function because then it's going to stay factored, right? So x minus 2 times the derivative of the top, which is what?
2x minus 2x. 2x minus 2.
minus top
Squared minus 2x plus 4
times
just that. Just
Yeah, just leave it
times
at
1, okay, divided by, no, x minus 2 squared is not x squared minus 2 squared. It's the quantity x minus 2 squared, right? That's different. Okay? So there it is. All right, so now what? Let's see. Can we do? No, we can't. Okay, so we've got to simplify this, right? So if we gotta FOIL this out, I guess, right?
Yep.
We can factor out a 2 there if we want. Well, no, let's just FOIL it out.
Keep going.
So what's that gonna give me? 2x squared
minus 2x
minus another 2x, so minus
That's
Or-
minus
4x
plus 4.
Wait, what?
No, you're
minus.
gonna be wrong.
No.
It's minus 6x.
Minus 6x, yeah.
It should be minus 6x.
Oh, you're right.
Yeah, you'll get 6x.
You're right.
Oh.
Minus x squared
Plus 2.
plus 2x minus 4, right? So that's on the top.
But there's more on the top.
Right, so we can cancel some stuff, right? We get those cancel,
Take away.
take away an x squared,
Take
and then,
away a 2 positive x.
so minus 4x on the top, is that right?
Yeah.
Right?
Yep.
Over x minus 2 quantity squared. So if we wanted to simplify that a little bit, we could take out an x times x minus 4 over x minus 2 quantity squared, right? Okay? Good?
Yeah.
Okay, while we're at it, let's do the second derivative. It's gonna be a little easier though, isn't it?
Mr. Oya, I
Yep.
just wanted to ask a question.
Oh, whoops.
Okay. No, it's okay, keep going.
You sure?
Yeah.
Okay. So second derivative, we'll just go ahead and differentiate from there, right? We don't want to, I mean, that'd be kind of ugly to do. There's no need to do a product rule within a quotient rule. Yuck. Right, we'll just do that.
I got you. No, okay.
Same.
So we get bottom times derivative of the top, which is what?
2x minus
Minus top
x squared minus 4x.
times derivative of the bottom.
2 and.
Yeah, I got you.
I'm lazy.
Divided by x minus 2 to the fourth, right?
Yes.
And then we could do a little factoring here, right? It looks like we could take out an x minus 2 from both of those two terms, right? And then cancel it with 1 on the bottom.
Yep.
Everybody see that?
Yeah.
Okay. So I combined it, we pulled out an x minus 2 and then canceled it with 1 on the bottom, right? Leaving us with
So it says?
some stuff. So we get, if we FOIL this out, we get 2x squared, what do we get here? Minus 4x plus 8. And then over here we get minus 2x squared plus 8x. Would you agree? Okay. Divided by x minus 2 cubed. Okay, that's easy though, isn't it?
Yeah, you can take it out.
Yeah. In fact,
Oh, 2x.
2x.
You get
Yeah,
8.
yeah, let me get 2 squared. You get 8.
right?
You okay, bud? No.
Okay, so now let's,
What about the negative?
did I forget a negative?
No, the
No.
positive 8.
I think
Well,
we're good.
if there's a positive 8x and a negative 8x.
Those cancel.
Oh, okay, okay.
Okay, so you guys write this down, because I'm gonna go to the next page and just summarize what these all were. So write that down for our second derivative. Write this down for our first derivative. Write that down for our function. Okay? And what was our, okay, I guess we need to know real quick, what are our critical numbers? We'll do that on the other page.
I'm just writing this down. 2. You're going right.
So we had the function, y equals what?
X squared.
2x.
Okay. We had y prime equals x times,
X minus 4, x minus 2.
and we had y double prime equals 8 over. Good. Put that quantity in there. Okay, so what's our domain? All real numbers except 2, right? Okay. Now this is important. What's happening at 2? And why? Okay, how come?
Zero.
Okay.
The bottom will be 0.
Bottom is 0. What is the top 0? No, so it's an asymptote. Right? Because remember, if we have simultaneous zeros, top and bottom, that's a whole. Right? 0 bottom, not 0 top means asymptote. So then we know that x cannot equal 2 in our table, which we're going to start to build.
Purple, right? Ready for this? You ready for this? It's gonna come quick.
This got harder.
You gotta be quick.
It's not super hard, but.
So
Hey, where'd you get 8 from?
I'll show you.
Just wait. Just wait.
That's where the function equals 0.
Well, it's where the function's undefined.
Oh, did you say the top equal to no? Where did he pull? I thought that was where did I?
Okay, everybody good at that?
What happened to 2?
Oh, 2. Sorry, was it 2?
Oh.
Okay, so which means I probably got to move that over to the.
Oh, it's fine. He's sitting there and he goes, oh, I'll show you. That guy. Pull on 8.
Whoops. Oh, hang on.
So we're gonna be able to finish this in 3 minutes?
I think so.
You have 3
Oh,
3
so.
minutes. Oh, gee.
Oh, I can do it.
You gotta be quicker than
You
that.
can.
Okay, gotta go fast.
There you go.
So we got.
I don't know why I'm coming up with this, guys.
So there's our vertical asymptote, right?
Yeah.
Okay, our zeros of the first derivative are at 4 only. And 0, right?
4 and 0.
4 and 0.
Got it.
So we get 0, 4, zeros of the first derivative, right? There are no zeros of the second derivative, right? And would everybody agree that the first and second derivatives are undefined where the function is undefined, so those are not critical numbers,
Exactly.
So then all we got to do is the second derivative test. What is the sign of the second derivative going to be when x is 0? It's going to be negative, isn't it?
Yes.
When x is positive 4? Positive. Okay, well, we know what that recipe is with the second derivative test. A horizontal tangent with a downward concavity. A negative function is frowny. Okay. Positive function, happy, right? And so what does this look like then? We know that we can put all this stuff together. So this is 0. So we get a relative maximum at 0. We won't worry about the values of y, we could. A relative minimum at 4. And we have the horizontal asymptote, or the slant asymptote, at y equals x. And an asymptote,
How do you know it was slant?
right there. Right?
He just.
Okay.
Wow.
Hey, ready?
Does that make sense?
No, how did you know it was slant?
We did. Hey, too much talking. This is too much. Listen, we're almost done here. So we did this earlier. Remember, we synthetically divided it. It's right.
Yep. X minus.
There, right?
X plus. Yeah.
So there's our slant asymptote. We get this y equals x. Okay. So when we go over to our graph, we can fill in the blanks. It turns out this point isn't here. Can't be, right? Because if the concavity is up, and we're going to stick to this asymptote,
Oh, yeah.
doesn't it have to be up here then?
Yeah.
It's got to do that. And on this side over here, it's got to be down here somewhere, because it's got to do this.
So it doesn't work.
No, it does. That's it.
Oh, what? So the point's fine though.
What's that?
So what's the point?
That's it.
It was fine.
The number answer. I don't think
Where
we're
did
gonna
you
do
get
it.
it?
What would the
Yeah,
count
say
math Excel?
your answer is just no.
Well, no, you can say, I guess you could say what those points are. Wow.
What's that?